Hey, welcome to The Explainer. Today we are diving deep into the world of polymers. They're literally everywhere, completely shaping our modern lives. But here's the thing, there are millions of them. So how in the world do we make sense of it all?
Okay, think about this for a second. You've got a plastic water bottle, a super tough car tire, and a soft cotton shirt. On the surface, they couldn't be more different, right? But believe it or not, they all share this one fundamental secret right down at the molecular level.
And that's it. The common thread is that they're all made of polymers. These giant molecules are the building blocks for so much of our world. We're talking everything from the natural fibers we wear to the super advanced synthetics inside our phones and computers.
So what exactly is a polymer? Well, the easiest way to think about it is like a super long train. Each individual train car, that's a small molecule we call a monomer. Now, when you link thousands or even millions of these little monomer cars together, you get a massive molecule, a macromolecule, and that's what we call a polymer. This long chain structure is what gives polymers all their amazing and unique properties.
But the sheer variety is just staggering. You can't just memorize every single one. So instead, scientists use a system of classification. You can think of it like a toolkit for understanding polymers. Each tool in the kit lets us look at a polymer from a different angle. And when we use them all together, we can build a complete picture of what it is and what it can do.
All right, let's open up our toolkit. The very first set of tools we're going to grab helps us answer two really basic questions. First, where does this polymer come from? And second, how is it actually made?
So, when you look at their origin, polymers fall into three pretty clear buckets. First, you have your natural ones, which you find in plants and animals. Think cotton, silk, or even natural rubber. Then you have synthetic polymers, which are cooked up completely from scratch in a lab, like nylon or polyester. And then there's this interesting middle ground, semi-synthetic. That's where we take a natural polymer and kind of tweak it chemically to make it even better.
Okay, our next tool is all about how we build these polymer chains. You can think of it like having two main recipes. In addition polymerization, monomers just keep adding on to the end of the chain, kind of like snapping Legos together. It's a really clean process. You use all the pieces, no leftovers. But then there's condensation polymerization. In this recipe, when two monomers join up, a tiny molecule, like water, gets kicked out as a byproduct. So the real difference is whether you get a byproduct or not. All right, so we know where they come from and how they're made. Now let's grab the next set of tools from our kit. We're going to zoom way in and look at the structural blueprints, how these long chains are actually arranged in three-dimensional space.
The absolute simplest arrangement you can have is a linear polymer. Just picture a single long strand of uncooked spaghetti. That's it. The monomer units are just linked end to end, forming one continuous, simple chain. Nice and straightforward.
But of course, things can get a lot more complex. You can also have branched polymers. So stick with our spaghetti analogy. Now imagine you've cooked it and it's all clumped together. You still have those main, long chains, but now you've got these smaller side chains branching off them. This branching is super important because it stops the chains from packing together really tightly, and that changes the polymer's properties, like making it less dense.
And finally, we've got the most complex structure of all, the network polymer. Now, this isn't just a few branches. This is a fully interconnected three-dimensional structure. Think of a fishing net, or maybe a piece of lasagna. Every strand is connected to other strands, forming this really strong, durable web. And all those connections, those crosslinks, that's what creates incredibly rigid and stable materials.
Now, even within those structures, the chains themselves can get organized in two different ways. In what we call crystalline regions, the polymer chains are all packed together neatly in a highly ordered repeating pattern. This order makes the material strong, rigid, and usually opaque. But in amorphous regions, the chains are just a tangled random mess, total chaos. This disorder makes the material more flexible and often transparent. And get this, most polymers are actually a mix of both. Okay, let's get even more detailed. Imagine our main polymer chain is a long piece of string. Now, imagine we're attaching little beads to it. These are called side groups. Well, tacticity is all about describing the pattern of those beads. If all the beads are attached to the same side of the string, we call it isotactic. If they alternate sides in a perfect pattern, one up, one down, one up, one down, that's syndiotactic. And if there's no pattern at all, if they're just stuck on randomly, that's atactic. This tiny detail, this geometry, has a massive impact on how well those chains can pack together.
Okay, we've looked at where polymers come from and their molecular blueprints. Now for the really fun part, the part that matters in the real world. Let's pull out the tools that tell us how they actually behave. This is basically their performance review.
One of the most critical classifications, especially for things like recycling, is how a polymer responds to heat. Thermoplastics are kind of like butter. You can heat them up, they get soft and melt, and then when they cool down, they get hard again. You can do this over and over. It's reversible. This is awesome for recycling. Thermosets, on the other hand, are more like cake batter. Once you bake it, that's it, you're done. If you heat it up again, it's just going to burn. The chemical change is permanent, which makes them really, really hard to recycle.
Next up, we can group polymers by their general physical properties, how they feel and act. Broadly speaking, they usually fall into one of three big families: elastomers, plastics, and fibers. Each one has its own distinct personality. So what's the difference? Well, it's all about how they handle being pushed and pulled. Elastomers are the stretchy ones. Think of a rubber band. You can stretch it out and it snaps right back. Plastics are the moldable ones. You can heat them up, shape them into something like a bottle or a chair, and they'll hold that shape. And then fibers are the strong, thin ones that we can spin into threads and weave into fabrics, like polyester or cotton. So we've now gone through all the major tools in our classification kit. But the real power here doesn't come from using just one of these tools. It comes from using all of them together to build a complete, detailed profile for any polymer we encounter.
Let's put this into practice with a really common material, PVC. You see it everywhere, in pipes, window frames, all sorts of things. So let's use our toolkit to build its profile. Where's it from? It's synthetic. How is it made? Through addition polymerization. How does it handle heat? It's a thermoplastic, which means we can recycle it. What's its structure? It's a linear chain that's mostly amorphous. And its overall property? It's a plastic. See? Just like that, we have this rich, multifaceted understanding of what PVC actually is.
And that, right there, is the key takeaway. Classifying a polymer isn't about just sticking it in one single box. It's about using this entire toolkit of different lenses, its origin, its structure, its behavior, to understand it from every possible angle. It lets us create a complete blueprint of the material.
Ultimately, what we've been doing here today is learning more than just a bunch of categories. We've been learning a language. This is the language that allows scientists and engineers to talk to each other precisely about these incredibly complex molecules, to predict how they'll act, and to design the amazing materials of our future. So I'll leave you with this thought. By understanding this toolkit, this language of classification, we're not just organizing the things that already exist. We are actually creating the blueprints for what's next. So what amazing new materials will we build tomorrow, now that we know how to speak the language today? Thanks so much for joining me for this explainer,